Welcome students, welcome to this thermal engineering session. This session we are going to see about the sources of energy. So under the sources of energy, this session we are going to see about the solar. So in the sources of energy, we are going to see about the brief description of energy sources, the classification of energy sources, renewable and non-renewable types, fossil fuels including CNG and LPG, and the solar energy. Under that, flat plate and concentrate collectors and its application, solar water, photovoltaic cell, wind and tidal and geothermal energy, biogas, biomass, biodiesel, hydraulic and nuclear energy, fuel cell and list of fuel cells. Now let's see the classification of energy sources. Energy sources are all forms of fuels used in the modern world, either for heating, generation of electrical energy, or for other forms of energy conversion process. Energy resources can be roughly classified in following categories: renewable energy, non-renewable energy, fossil energy, and nuclear energy. Renewable energy sources are forms of energy that are naturally replenished on our planet. Examples of traditional renewable resources are hydropower and biomass. Example, plant fuels such as wood traditionally have been used throughout history, mostly for heating. And modern renewable resources include wind, wave, tidal, solar, and geothermal. Some forms of fuels created from biomass, plants and animals also falls under this category. And what are the non-renewable energy sources? This non-renewable energy comes from sources that will run out or will not be replenished for thousands or even millions of years. Most sources of non-renewable energy are fossil fuels. So fossil fuels were created as the remains of marine creatures decayed millions of years ago under huge amounts of pressure and heat. Most fossil fuels are burned to create energy and electricity. Coal above is a type of rock that is a fossil fuel. Now let's come to the solar energy application. It's a one type of renewable energy applications. Solar energy, under the solar, we are going to use two types of energy from the solar. From solar, we are going to use heat as an energy and light also as a one form of energy. From solar heat energy, we are going to use a flat plate and concentrating collectors and solar water heater, solar distillation, and from that solar light energy, we are going to have the solar photovoltaic cell, solar flat plate collector. So this is the layout of solar flat plate collector. A typical flat plate collector is a metal box with a glass or plastic cover called glazing on top and a dark colored absorbed plate on the bottom. Sunlight passes through the glazing and strikes the absorbed plate, which heats up, changing solar energy into heat energy. So this is the layout of the solar flat plate collector. When the solar radiation incident on it, into that inside this solar flat plate collector, a long collection of long tubes are arranged in parallelly so that the water from the pump flows through it. It gets heated up and it's converted into steam or the hot high temperature fluid. It's again come back to the storage tank. In the storage tank is the heat exchanges takes place. So this is the primary storage tank, and this is a secondary line. From this primary storage tank, the heat is transferred to the secondary line through another fluid. Then the fluid gets vaporized, and this vapor form will enter into the steam turbine, and it runs the steam, steam turbine, which is coupled with the generator so that it produces electricity. Then from the steam turbine, the remaining vapor gets the the expanded vapor form will enter into the condenser, so it gets condensed, and again this working fluid is pumped into the vapor generation secondary system. Now let's see the solar thermal collector collects heat by absorbing sunlight. The term solar collector commonly refers to a device for solar hot water heating, but may refer to large power generating installations such as solar parabolic traps and solar towers or non-water heating devices such as solar air heaters. Solar thermal collectors are either non-concentrating collectors or concentrating collectors. Let's see about the concentrating collectors. It has a much bigger aperture than observer area, that is additional mirror focus sunlight on the observer, and only harvests the direct component of sunlight. Concentrating collectors in concentrated solar power plants generate electricity by heating a heat transfer fluid to drive a turbine connected to an electric generator. So this is how the layout of the concentrating collectors looks like. So this is a, here it is a parabolic trough collectors. In this parabolic trough collectors, all those instant light is focused in the center where the evacuated tube is there. In the inside that the fluid is flowed through it, it gets heated heated through the focused sunlight, so that it gets converted into steam. That steam is used to run the turbine. While running the turbine, it is coupled with the generator so that it produces electricity. And from the turbine, the expanded steam is condensed, and again it goes back to convert to steam. Now let's see the small video about how this solar concentrating collectors works.
Okay, take the natural heat from the sun, reflect it against a mirror, focus all of that heat on one area, send it through a power system, and you've got a renewable way of making electricity. It's called concentrating solar power, or CSP. Now, there are many types of CSP technologies: towers, dishes, linear mirrors, and troughs. Okay, have a look at this parabolic trough system. Parabolic troughs are large mirrors shaped like a giant U. These troughs are connected together in long lines and will track the sun throughout the day. When the sun's heat is reflected off the mirror, the curved shape sends most of that reflected heat onto a receiver. The receiver tube is filled with a fluid. It could be oil, molten salt, something that holds the heat well. Basically, this super hot liquid heats water in this thing called a heat exchanger, and the water turns to steam. Now the steam is sent off to a turbine, and from there, it's business as usual inside a power plant. A steam turbine spins a generator, and the generator makes electricity. Once the fluid transfers its heat, it's recycled and used over and over, and the steam is also cooled, condensed, and recycled again and again. One big advantage of these trough systems is that the heated fluid can be stored and used later to keep making electricity when the sun isn't shining. Sunny skies and hot temperatures make the Southwest U.S. an ideal place for these kinds of power plants. Many concentrated solar power plants could be built within the next several years, and a single plant can generate 250 megawatts or more, which is enough to power about 90,000 homes. That's a lot of electricity to meet America's power needs.
Concentrated solar power uses thousands of mirrors to reflect and concentrate sunlight onto a central point to generate heat, which in turn is used to generate electricity. More than 10,000 tracking mirrors called heliostats reside in a 4 square mile field where they reflect and concentrate sunlight onto a large heat exchanger called a receiver that sits on top of a 550-foot tower. Within the receiver, fluid flows through the piping that forms the external walls. This fluid absorbs the heat from the concentrated sunlight. In this technology, the fluid utilized is molten salt, which is heated from 500 to over 1,000 degrees Fahrenheit. Molten salt is an ideal heat capture medium because it maintains a wider operating temperature range in liquid state, allowing the system to operate at low pressure for superior and safe energy capture and storage. After passing through the receiver, the molten salt then flows down the piping inside the tower and then to a thermal storage tank where the energy is stored as high temperature molten salt until electricity is needed. This technology leverages liquid molten salt as both the energy collection and the storage mechanism, which allows it to separate energy collection from electricity generation. When electricity is required by the utility day or night, the high-temperature molten salt flows into the steam generator as water is piped in from the water storage tank to generate the steam. Once the hot salt is used to create steam, the cool molten salt is then piped back into the cold salt storage tank, where it will then flow back up the receiver to be reheated as the process continues. After the steam is used to drive the steam turbine, it is condensed back to water and returned to the water holding tank, where it will flow back into the steam generator when needed. The result is a high-quality, superheated steam to drive the standard steam turbine at maximum efficiency to generate reliable, non-intermittent electricity during peak demand hours. The steam generation process is identical to the process used in conventional gas, coal, or nuclear power plants, except that it is 100% renewable with zero harmful emissions or waste. These plants provide on-demand, reliable electricity from a renewable source, the sun, even after dark.
So now comes the solar thermal collectors, the non-concentrating collectors. The aperture area, that is the area that receives the solar radiation, is roughly the same as the observer area, that is the area observing the radiation. This type has no extra parts except the collector itself. Non-concentrating collectors are typically used in residential and commercial buildings for spacing, heating, and domestic. So this is a non-concentrated solar collectors. For example, solar water heater, which we are used in a domestic applications. Here, this is the solar collector, which collects the solar heat energy, so that it heated the water and it stored in it get transferred in the boiler setup. Okay, so that from this tank we can heat exchange the heat to the normal domestic water, and which can directly send to taps, or we can store in our normal geyser tank. Okay. Solar water heater, that is non-concentrated type of solar collectors. Let's see the solar flat plate collector and its application. The flat plate collectors typically consist of copper tubes fitted to flat observer plates. The most configuration is a series of parallel tubes connected at each end by two pipes, the inlet and outlet manifolds. The flat plate assembly is contained within an insulated box and covered with tempered glass. Flat plate collectors are typically sized to contain 40 gallons of water. Two collectors provide roughly half of the hot water needed to serve a family of four. Let's see the advantages of solar heat energy. So water heating bill savings, having a low maintenance, environmentally friendly, almost limitless source of energy, and it does not produce air pollution. And even though we're having advantages, some of the disadvantages of solar heat energies are high upfront installation costs, dependent on climate, only practical in sunny areas, only heats water, expensive to use for large scale energy production. Solar distillation. We know that the distillation is the process of converting the pure water from the mineral water. Okay, so how we are going to use the solar energy for distillation? So this is the distillation setup, solar distillation setup. This is the glass, clear glass or plastic to transmit radiation from sun, and to inside is used to condense a vapor. So this is the basin, and inside this is brine water or brackish water or the salt water which we fill in, and the two side we are giving the distillate or condensate trough. Okay, so that the condensed water is coming collected and will get collected outside. So what are the four basic elements needed in a solar cell? One is, first is the incoming radiation, that is the energy, and water vapor production from brine water, condensation of water vapor, that is for condensate, and collection of condensate. So when the sunlight is incident on the glass or plastic plate, it transmits the radiation into the water, so that the water get heated up and the water get vapor converted into vaporization. So that's water vapor which can't escape out of this basin, so that this water vapor is going to collected in the glass, inside part of the glass, so that the water vapor become now condensed to form the vapor particles, water particles. This water particles sliding down and collected in the distillate, so we will get the pure water. It means only the pure water get vapor up, get vaporization and vapor evaporate up. This evaporate is condensed and collected here, and the remaining salt water or salt particles is left behind in the basin. A solar still distills water with substance dissolved in it by using the heat of the sun to evaporate water, so that it may be cooled and collected, thereby purifying it. They are used in areas where drinking water is unavailable, so that clean water is obtained from dirty water or from plants by exposing them to sunlight. There are many types of solar still, including large scale concentrated solar stills and condensation traps, better known as moisture traps amongst survivalists. In a solar still, impure water is contained outside the collector, where it is evaporated by sunlight shining through clear plastic or glass. The pure water vapor condenses on the cool inside surface and drips down, where it is collected and removed. A solar cell or photovoltaic cell is an electrical device that converts the energy of light directly into electricity by the photovoltaic effect, which is a physical and chemical phenomenon. It is a form of photoelectric cell defined as a device whose electrical characteristics such as current, voltage, or resistance vary when exposed to light. The individual solar cells devices can be combined to form modules, otherwise known as solar panels. The common single junction silicon solar cell can produce a maximum open circuit voltage of approximately 0.5 to zero point 0.6 volts. The operation of a photovoltaic cell requires three basic attributes: the absorption of light, generating either electron-hole pairs or excitation, the separation of charge carriers of opposite types, the separate extraction of those carriers to an external circuit. Let's see the video of the solar photovoltaic power system, how it works.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the P-N junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the N side, while the hole is drawn to the P side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
Now let's see the advantages of solar photovoltaic energy. Electricity produced by solar cells is clean and silent. Photovoltaic systems are quiet and visually unremarkable. Small scale solar plants can take advantage of unused space on rooftop of existing buildings. PV still powers nearly every satellite circling the Earth because it operates reliably for long periods of time with virtually no maintenance. Solar energy is a locally available renewable resource. A PV system can be constructed to any size. Now let's see the disadvantages of energy solar photovoltaic energy. Location and sunlight availability and your latitude is one of the main factors in determining the efficiency of solar power. And installation area, reliability, inefficiency, pollution and environmental impact, expensive energy storage, and high initial cost. And these are the disadvantages of solar photovoltaic energy. Thank you, students. Thank you for watching this video. Let's see in the next class remaining sources of energy.